Alright, welcome back, MATH1720. We are still in Chapter 7. A couple sections ago here, we're in Section 4. We are going to go over geometrically defined vectors and applications of them. So this might be your first time talking about vectors. You've had a physics class maybe, you did some vector analysis in there. We'll also hit vectors again in calculus. So just kind of different things. This should start honusing in on your vector analysis. So the first things that we're going to get through is a lot of terminology and just understanding some basic vocabulary for vectors and things like that. So scalar, we're going to apply this to vectors as well, but you've also done it with like a linear equation, right? Like 2x times 4x, or 10x or something like that. So scalar, kind of what it is, it's the magnitude of a quantity, all right, and we can represent it with a real number. A vector, okay, is just in a plane. It's a directed line segment, not a line, but a line segment. So we go from point A to point B, or that sort of thing, from point B to point C. We have finite ending points when we go through it. And how we label a vector. So this is vector OP, and we draw an arrow over the vector to indicate which direction we're going. So when we draw a vector, we have an initial point and a terminal point. So in this particular vector, the initial point is O. That's where we start the vector from. All right. And then we have P, which is the terminal point. Sometimes you might hear it head and tail. So P would be the head, O would be the tail. Physics, they talk about it a little bit that way as well. Okay. The magnitude, okay, that's the length of the vector. So that's the entire length of it. Two vectors are equal if and only if they have the same magnitude and the same direction. That's the important part. They must have the same magnitude and the same direction. They have to be going the same exact way. So if we look at vector OP and vector PO, okay, their magnitudes are different here. Okay, they're going in opposite directions. So regardless of if the magnitude is 20, okay, let's throw a number out there. Let's say the magnitude is 20, okay? One is going up and to the right, the other is going down and to the left. So they have the same magnitude, but they have opposing directions. So they're not equal. So let's look at A and B here. A and B equal, right? Same length, same direction. C and D equal, same length, same direction. E and F, okay, or I'm sorry, yeah, A and E, sorry, comparing here. They might be the same length, they are not the same direction, so they do not equal each other. And A and F, same direction, not the same length, so that's why A and F are not equal to one another. Okay, so make sure that we understand that. When we add vectors, we're going to be able to add, subtract, dot product, do those sort of things. Okay. The sum of two vectors is also a vector. All right. So if we add two, now what you call that, there's a specific name for it. We call it the resultant. All right. So the vector sum is a resultant. So we're going to get into some examples here. And in physics class, you talk about forces acting in different directions, and you want to find the resultant vector. All right. The vector that comes about because of two other vectors. So a couple of different ways we can represent this, all right, and we got to get back to like our parallelogram days and things like that. So we can see that in the left hand side we have vector A and vector B. When we add those, we get the resultant vector. We can also draw A and B as such on the right, all right, and make the resultant vector the diagonal of a parallelogram. So very, very important. We are going to be applying the law of cosines to solve like the resultant vector, right? If I give you a magnitude for A and B, and I give you the angle, you can use the law of cosines to find the vector resultant for A plus B. So remember, on your assignment or the test asks for you to find the resultant, you need to do the vector sum. All right, this is another one here. The sum of vector V and its opposite V, so negative V. Remember, negative is not a quantity in this case. The magnitude is always positive, but the direction can change. All right, so the magnitude will always be positive because it's a distance. All right, the negative represents the direction. So when we have the sum of a vector and its opposite, the magnitude, the resultant, is a zero vector. Okay, so if we want to subtract vector b from vector a, we have to find the vector sum of a plus negative b. Does that make sense? We have to find a plus its opposite, the opposite of b. Hopefully that should make sense there. So if we're looking for something on the left-hand side, we're going to do an example here that incorporates the opposite vector, so you're going to have to be able to understand that and calculate. Okay, so scalar, right, just a multiplier of what we're really doing. So we can take a number k, all right, k is going to represent a number, and we have a vector u, so we can just multiply. So we're multiplying the magnitude by some sort of scale. So if we look down below, we have vector u, and then we have the vector 2 times u, right? It's twice as long as u. We have the vector 3/2 u. It's 3/2 times u. We have the vector 1/2 u. So on and so forth. We should just know that a scalar is just a multiplier to the magnitude of that vector. All right, reviewing parallelograms. Okay, remember parallelogram is a quadrilateral whose opposite sides are parallel. Okay, the opposite sides and opposite angles are also equal, and adjacent angles of the parallelogram are supplementary, meaning they add up to what? 180 degrees. Those are the adjacent angles, the angles that are next to each other. Okay, and the diagonals of the parallelogram bisect each other, but don't necessarily bisect the angles of the parallelogram. That's an important one because everybody seems to think that the angle perfectly bisects there. Okay, that would be the diagonal of a square that does that, not a parallelogram. Now in the middle, the diagonals, so if you draw from one corner to the other and draw from the other corner to the opposite corner, in the middle, the diagonals perfectly bisect those, okay, each other, but the angles don't. All right, so let's do an example here. All right, so make sure you pause the video, write this one down, have this one in your notes. All right, we have two forces, a 15 and a 22 Newton. Okay, they act on a point in a plane. A Newton, if you don't know, it's a unit of force, it's 0.225 pounds. Okay, if the angle between the forces is 100, find the magnitude of the resultant vector. Always, vectors, very simple if you can draw the sketch and understand what's going on. So we need to draw two lines essentially on a piece of paper with 100 degrees between them. Label one of them 15 in length, the other in 22 in length. Now you've drawn, okay, a vector or a force diagram. Now you can calculate the resultant vector. Note the resultant vector is going to lie in between those. So you should sketch something like this. It turns out that it works out well that it's a parallelogram, hence that's why we went over parallelograms. So you can see, okay, what I asked you to draw before, doing this problem was PS and PQ. Did I tell you to label those? Nope. You can label those whatever you want. AB, ABC, ABCD, XY, WXYZ, whatever you want. Okay, the labeling doesn't necessarily matter. It's only if it's given to you. But you do have to make sure that what you're seeing in blue is how you drew this. All right, you have two lines that are 100 degrees apart. Okay, and you may not have even drawn it. This is a portrait. You might have drawn it landscape. That's completely fine as long as we're showing everything correctly in the sketch. So what does it help us for being a parallelogram? Well, it helps us solve different aspects of what we need, because we want to be able to apply the law of cosines. So if we just drew it with what's in blue and what's in purple or pink, whatever color you want to call them, all right, we wouldn't have necessarily enough information. But by completing the parallelogram, we create the necessary triangles that we need to use tools that we have. Law of sines, law of cosines, any of those different tools that we can use to finish solving. And because of the rules of parallelogram, if we use a parallelogram to make the triangles that we need, we know that it holds true for the other side of the parallelogram. So we're using kind of all these terms together to complete this. Okay, so what we need to know is, if that's 100 degrees, we know that in a parallelogram, right, the adjacent angles are supplementary. So we know that if angle QPS is 100, we know the other angle PQR has to be 80. So does angle S down there, all right? Because their opposite angles of a parallelogram are equal. So just note that. That's why it's really important that we can draw parallelograms out of all these, because it tells us certain lengths and certain angles that we need. And understanding, the properties of parallelograms is really key here. Okay, knowing, if you don't know that those two angles, the adjacent angles, are supplementary, you're not going to figure out that the other angle is 80 degrees. So it's very, very important. That 80 degrees helps us out a lot. All right, so let's continue on with solving this one. So we're going to apply the law of cosines. Law of cosines, and remember, it's not going to go across the parallelogram. We're going to apply the law of cosines to the triangle that's on top and to the right. Okay, so we're going to look at triangle PQR when we do this. Why? Because it's across from that 80-degree angle. We can also do it in terms of PSR as well. Doesn't matter, because we have the angle opposite the side we need. The side we need is V, right? The vector magnitude, that's what we're looking for. And then we have 22 and 15, and 80 is between them. So we could literally use either one of the triangles using the law of cosines. It'll work out the same. So we substitute into the law of cosines. So instead of now, A, B, C, we have, our different vectors that we're going to apply. So the magnitude squared is equal to 15 squared plus 22 squared minus 2 times 15 times 22 cosine of 80. Just remember, please make sure, your calculator's in degrees mode when we go through these. And you approximately get 594 for that. Now, does that answer make sense? Nope, we got to square root that answer and get 24. Okay, so make sure that you're using your calculator, substituting incorrectly, and you're getting these values that I'm showing you here on the examples. All right, if you're not, let me know, and we'll make sure that you know how to substitute this stuff into your calculator correctly and get it. Your calculator is a nice tool here for you. All right, so how does this work out? We call it the magnitude of the resultant vector is about 24 newtons. And, newtons, very common, measurement that we use as part of the metric system, things like that. A lot of the stuff that you're going to do in physics, if you haven't already taken it, or if you're going to take it, is going to deal more in newtons instead of using imperial foot-pounds and things like that. So, magnitude of the resultant vector is 24 newtons, and we keep it in newtons because the 15 is in newtons and the 22 is in newtons. Okay. Let's talk about the equilibrium, right? Sometimes it's necessary to find a vector that's going to counterbalance the resultant. We call the opposite vector the equilibrant vector. Okay, so if we have a vector u, okay, negative u is its equilibrium vector. All right, so let's move forward here. We're going to apply that here. We want to find the magnitude of the equilibrant of forces of 48 newtons and 60 newtons acting on a point A. If the angle between the forces is 50 degrees, find the angle between the equilibrant and the 48 Newton force. All right, so you're going, what does all that mean? All right, well, we'll read into it and then we'll draw a sketch. Always draw a sketch the best you can. Okay, so draw the sketch as such. The first thing you should start with is AB here and AD. You can't, it's not labeled D, but just know the bottom one's D. Okay, so in here we have those two forces. We have the resultant vector that always goes between them. It'll be the diagonal of the parallelogram. All right, and if we know the angle between the forces is 50 degrees and we draw the parallelogram, we know that 50 is supplementary with the other angle, angle B up there. So that becomes 130. So we take 180 minus 50 to get you 130. So now you have some angles that we can work with. Now, what you need to understand, that 50 does not necessarily divide into 25 and 25. If it did, this problem would be super easy, but it doesn't. So don't ever assume that that 50 is being bisected and is 25 and 25. It's not. Okay? Then we want to find the angle between the equilibrium and the 48 Newton force. So you have to draw the equilibrium, okay? So what you did first is you drew AB, then you drew AD, then you drew the resultant vector AC, and we call it vector V. That's the resultant vector. Then you have to draw the equilibrium vector. That's the negative vector that's pointing to the left, okay? Now that you've drawn that and it makes sense, all right, the equilibrium vector is always the opposite vector, opposite direction, same magnitude, opposite direction. Okay, now we can draw this, and we've shown the angle alpha in between, because the question says, then find the angle between the equilibrium, which is the negative V vector, and the 48 Newton force. So angle alpha drawn up here is exactly what that is. All right, so now that you're able to draw the sketch, and what you should do is, cover up the sketch and redraw the sketches multiple times based on the verbiage till you get good at drawing a sketch, because these problems are hard if you can't draw them, and you need to be able to draw the vectors out to understand how to solve them. These are not problems that you're necessarily going to be able to do 100% in your head. If you can draw all these vectors and figure this all out in your head as you go, that's awesome. You are ahead of the game. All right, so let's solve this guy. The magnitude of V is the same as the magnitude of negative V, right? So we can substitute in here. We're going to use that magnitude of negative V here in a second. But we have to find what V is. So now that we've drawn our parallelogram, we are applying the law of cosines. We're applying the law of cosines to find V. Okay? Because we need V to find negative V, or the opposite V. And we need the opposite V to help find alpha, because alpha is the angle between the 48 and the negative V. Okay, that's the angle. That's what we're really solving for. Here's what alpha is. So when you substitute in the values, we get the sum vector, or the resultant vector, is 98 newtons. Okay, so the next step is getting, all right, the opposite vector, that negative V, okay, the equilibrium vector. All those different names mean the same thing. So we know that it is also 98 now, though, because the vector V is 98. It's just 98 in the opposite direction, right? I mean, does it really matter if you drive 10 miles east or 10 miles west, right? You drove the same amount. You drove 10 miles east or you drove 10 miles west. Just different directions. So I want you to think about that as kind of how the magnitude works. Okay, so we have to find, it's mislabeled on here. It says the required angle theta. It should not be theta. That is the angle alpha. So we've got a typo in here. It's angle alpha. Okay, so we can subtract and find alpha by doing some calculations. We need to use the law of sines. All right, but we have to, we'll subtract it from alpha here in a sec, or from 180 here in a second. So if we use the law of sines here, why are we using the law of sines? Well, because we need to find the angle, and I'll step back a slide. If we can find CAB, because remember I told you that the 50 does not necessarily split into 25 and 25. So you cannot assume that CAB is 25 degrees. We have to actually calculate it. And then once we calculate it, we can do 180 minus that to get alpha, because they are supplementary angles. All right, they add up to 180. So when we do that, we're going to use the law of sines to find CAB. I'm not going to get into the details on this piece because we've done, the first two sections in this chapter on the law of sines, and then we did some in the last chapter, or the last section's lecture with the law of sines as well. So you should know how to solve for the law of sines here. So to get the angle, though, remember, that's the ratio. So sine of CAB is 0.469000680. You have to do sine inverse of that value to get the angle. Make sure your calculator's in degrees mode and you hit second sine and type in the 0.469. You should get about 28 degrees. Now that we know that that's actually 28 degrees, we can take 180 minus 28 to get alpha. All right, so when we do that, alpha ends up being 152 degrees. This is a really, really good problem. What I think you should do is, after taking notes on this, you may or may not do this, but a study tip, rework the example problems that I give you. So, study tip, all right, rewrite the problem down and see if you can resolve it without looking at any of your notes. That's going to tell you if you've got a good grasp on it. It'll really help you, just get in the habit of being able to draw these. I think half the battle is being able to draw your vectors and then just kind of piece things together. Draw your vectors, make your parallelograms, Then you got to figure out what exactly am I solving for in this problem. Because it's going to be based on interpreting like the language, the paragraph, and understanding what the problem's asking with a lot of these. All right, let's get into some physics now. All right, we're going to find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees. All right, well, for me, that just means put a block of wood behind it, right? So it doesn't go anywhere, but we got to do some calculations here. So this picture is very, very important that you understand how to draw it. There's a lot of different things that we're pulling in here. Now, the wagon is 50 pounds. It's acting at a vertical or perpendicular, straight down. So when you look at the vector diagram below, the 50 pointing down, that's the weight of the wagon. Okay, we're not going to include gravity in this calculation. Eventually in physics you'll have to do that. This is also really big in statics and things like that as well, being able to solve these vectors if you go into civil engineering or things like that. Okay. Now, it's sliding down a ramp that's inclined at 20 degrees to the horizontal. So that means, right, we have our horizontal. You can see where the 20 degrees there on the left-hand side. That's how high the ramp is. Now, we really have to figure out, how do these other angles come into play? How do we know that angle ABC is 20 degrees as well? All right, there's some relationships that we have to develop with these triangles. Notice the triangles have a perpendicular, okay? That comes into play as well. So try to draw everything as perpendiculars. So we want to find, okay, the force keeping the wagon from sliding down the ramp. So the force vector shown there in the pink or purple, whatever color you want that F. Okay. So the vertical force, okay, that's the force, the weight of the wagon. We're going to incorporate gravity into that. I said we're not going to incorporate gravity, but remember gravity's 9.81 meters per second or things like that. That's acceleration due to gravity. All right. We're going to throw that all into one here. There'll be different things that you get into later on that have moments and that sort of thing. All right. So the vertical force is BA. All right. So we have BC plus negative AC when we do that. So BC, if you take a look at that, and then we have what? Plus negative AC, because we're really finding the opposite vector there, okay? When we do this. BC represents the force with which the weight pushes against the ramp, okay? So that's our BC. The wagon literally just sitting there, it's at rest, pushing on the ramp. So that's vector BC. Vector BF, that's the force representing that we need to pull with, right? If you're pulling the ramp like or the wagon up the hill or something like that. Okay, this doesn't include if there's a load in the wagon or anything like that. So we really just need to make sure, I'm going to step back here. We understand that BC here is representing the force, okay, downward. So then we have to represent the next one, right? BF, that's at the angle going up the ramp. So if we take a look at vectors BF and AC, they're equal to each other, okay? They're going in the same direction and they're the same length, okay? So they have the same magnitude as we work through this problem, okay? Now, here's the really, really important piece for us. Vectors BF and AC are parallel. Very important that we're going to do this because we're going to pull in some geometry here. Vectors BF and AC are parallel. So that tells us that the measure of angle E, B, and D, E, B, D, equals the measure of angle A. Because why? We have two parallel lines cut by a transversal. The transversal is BD. So two parallel lines cut by a transversal, alternate interior angles are equal. So do we 100% have the values for those? Yes, we have the value now for EBD, right? That's in a small triangle. That's in triangle EBD, all right? And we know the angle EBD is now what? Okay, it's 70 degrees because that triangle is a 90-degree triangle. So all the angles have to add up to 180 degrees. So 180 minus 90 minus 20 is 70. So that means angle EBA is 70, which also means BAC is 70, which is why angle ABC is 20. So it's very important that we understand that. All right, so we have to draw all the different forces acting down. It's very, very important when we draw these out. These are probably the hardest ones that you're going to have to work through and figure out. Okay, so I just kind of walked through all that and explained why that angle is 20 degrees. So how does that help us? Well, we can use what? Knowing that it's a right triangle, we can find the force vector AC, and we know it's the same as the vector BF. Okay, so we're finding something, and it's not necessarily even on the picture piece that we want. We're just finding its equivalent. All right, so we know sine in a right triangle, right? Because triangle ABC is a right triangle. Sine is opposite over hypotenuse. So we know that vector BA is 50. That's the hypotenuse of the right triangle. So sine of 20 is AC over 50. So really AC is just 50 times sine of 20, which is 17. All right? So the force of 17 pounds will keep the wagon from sliding down the ramp. So you got to hold that with about 17 pounds, right? Now, this is a really important problem. So, like I said with the last one, I'd like you to do the same with this one. Write the problem down again and rework it without using your notes. Rework this example. You'll really gain a stronger understanding. Part of understanding is learning how to study. And you learn how to study by reworking problems multiple times so that you get good at them. Okay? It's like video games, right? You don't play it once and then you're done and whatever, right? You want to win, you want to get good, so you play it over and over and over and over. You'll play the same round 1,000 times or more, right? You got to do the same thing with math. Not literally 1,000 times, but you do need to practice. All right, so let's do another problem here. Now we want to find an angle. Okay, we're going to find theta. Same setup with the ramp. You're going to notice that the ramp is going to set up the same way with the ramp problems now. Only we're going to work backwards and find theta. You should automatically, I kind of already know and see where I'm going to go with that. So this problem shouldn't be as intimidating now after we kind of forced our way through the last one. And we're going to find out, right, what relationship does angle theta have to any other angles up here. Okay, so we have a force of 16 pounds is required to hold a 40-pound lawnmower on an incline. What angle does the incline make with the horizontal? All right, so we have a picture here for us, which makes it like 1,000 times easier. Make sure that you do draw the picture. So just knowing from the last problem, right, if BE and AC are parallel lines, we have two parallel lines cut by a transversal. That transversal is BA. That tells us what? That angle B up there inside the triangle is the same as angle BAC, right? Alternate interior angles are equal. And then we can take 180 minus 90 minus what angle B is, and that'll give us theta. So we can work through this. All right. The first part is we only have, two parts to our triangle though. So that's the biggest key there. We have a 40 and we have a 16-pound force. Just to note, BE is also a 16-pound force up there. Remember, BE and AC are the same thing. So very, very important. All right. So in the right triangle, I just kind of walked you through how the relationship works. Let's get through the meat and potatoes here. So we need to find angle B at the top. Okay, so that'll help us find BAC, which will relate to the other angles. Okay, so B, note this is a right triangle, and make sure your calculator's in degree mode. So sine of B is opposite over hypotenuse. We can see the hypotenuse is 40, the opposite is 16. So sine of B is 0.4, so you have to do sine inverse of 0.4 to get 23.6 degrees. So that is not our theta. That's angle ABC technically. All right, angle ABC is 23.6. Now we have to know the hill makes an angle of 23.6 with the horizontal. Okay. So that angle ABC is the same exact angle as theta. So that's why we can conclude the hill makes the angle of 23.6 with the horizontal. So it's just like the last problem, all right? This one looked scarier, but was like 10 times easier, all right? Just using the vector analysis, using law of sines. And we had enough given in this problem to actually find the angle, okay? So a couple different ways we can walk through it, all right? I've thrown multiple ones at you, but this was the simplest way to solve this problem. All right, let's do another one. So this is going to be our most common one. All right, we got vectors and traveling, and we got to remember how we use bearings and things like that. So notice the method of bearing that we're going to have in this problem. I'll reiterate that here in a second. It says, a ship leaves port on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels 4.3 miles. How far is the ship from port? What is its bearing from port? Okay, so two different things. We've got to find a distance. Okay, so that's the purplish pink line there, PE. And then we got to find the angle. Okay, what's its bearing from port? From port, that's the important part, is from point P. Now, reviewing bearings, this methodology, if we just have a bearing and we have a specific degree and that's it, it's not doing right to the south or to the east or to the west or that sort of thing, we are starting always facing north. If you guys remember that, I think that was chapter 3 where we went through the bearings. All right, so we're going to start facing due north, and a bearing of 28 degrees means we're going to be facing north, and we're going to turn 28 degrees clockwise. All right, so it turns 28 degrees clockwise and travels 8.2 miles. Then at that point, point A, it turns due east. Remember, due east is exactly east. All right, so it'll be on that perpendicular for 4.3 miles. All right, and then we want to calculate from port, so that's the vector PE. Okay. Important part being is how does that 118 come about? All right. Well, notice if we look at triangle P going up to N where the north piece is over to E, that's a right triangle. Okay, so we can say that we can take 180 minus 90 minus 28, all right, which gives us what? 62, correct? Then we know that that 62 is supplementary with the 118 degrees there because the segment AE is 180 degrees, which is a straight line. So if we go from where that dot is, where N is, over to E, we know that that's a straight line, okay? And so we know that we have that 62 degree angle right there. And let's see, 20. So yeah, 62 degrees. So that's how we know that, okay? So angle, if I'm calling it point N, so the angle between N, A, and P, that's where our 62 degrees is. So that's how we make that 118 to make that 180 degrees. So it's very important that we find that 118 degrees because now we can use the law of cosines to find the vector PE, the distance the ship is from port. So very, very, very important how we do that and how we calculate that. Okay, so using that 118 degrees and the law of cosines, because we know the one distance is 4.3, the other distance is 8.2. We substitute into the law of cosines, making sure your calculator is in degree mode. All right, and we get that PE squared is 118.4, so we got to square root that answer. You should approximately get 10.9. So the vector PE is 10.9 miles. Okay, now that we know that it's 10.9 miles, we're able to use that information to help us find the small angle that we need, that we have to add to the 28 to find its bearing from port. Okay, so if we do that, okay, we want to find APE. That's the little angle, and then we're going to add that to 28 to figure out its bearing from port. So we're going to use the law of sines in this case. So we're going to take sine of APE over 4.3, all right, equals sine of 118 divided by 10.9. That's the vector distance that we calculated. So when you do that and you solve for sine of APE, all right, we should be able to do that. And remember, you got to do sine inverse. We should approximately get 20.4. So now we have to take the 20.4 plus the 28 degrees, and that'll give us its bearing from port. Okay, so we're finding that very small angle there, so the bearing from port is 48.4 degrees. Okay, so relatively, you're gonna have multiple problems that are as simple as this one. This one, we just got to walk through the steps. Remember, when we do bearing problems, to always draw your north, south, east, and west at each turning point that you make. That'll really help you solidify what the angles are there, and it'll help you visually see what the angles are and how to find them as you work through the problem. Alright, so let's talk about flying a plane. Alright, we got airspeed and we got ground speed. So airspeed, that's the plane's speed in the air. Relative to air, there's ground speed. It's speed relative to ground. Alright, and the ground speed of a plane is represented by the vector sum of the airspeed and wind speed vectors. Alright, so this is important. This is how airplanes fly. They got to correct based on, whether they got a headwind, tailwind, or wind coming at them from the side. So they have to correct their angles so that they stay on course and maintain the right direction. So very, very important. So we have to make sure that we understand, alright, what the bearing and airspeed are, what the drift angle is, what the wind speed is. Alright, so you can kind of see it all laid out for you right there. How when a wind hits, the front of the plane and how it turns the plane, how you got to correct the plane before the winds. Because there's different winds, at different levels of the atmosphere and things like that. Alright, so let's write this problem down. We got an airplane that's following a bearing of 239 at an airspeed of 425, encounters a wind blowing at 36 miles per hour from a direction of 115 degrees. Find the resulting bearing and ground speed of the plane. Okay, so this is important that we draw our little north, south, east, west, and when we draw our problem out here and how everything is being impacted. Alright, so first draw your plane. It's a bearing of 239. So you're going to be drawing north, and then you're going to go 239 degrees clockwise as you get down there. And then from there, we're going to draw the wind at the end of that and show how it's affecting it. Okay, so if we take a look, the airplane one is in the upper right-hand corner. Alright, so we started facing north, and we rolled around 239 degrees clockwise. Alright, and then we have our airplane. So that's the blue vector that you see up here. Then we have a wind. So at the head of that vector, okay, the last part of that vector, AB, where the plane's going, we draw another north, south, east, west, and we draw what the wind is doing. Okay, the wind is coming what? 150 degrees, or 115 degrees, sorry. So we draw the bearing of 115 degrees from the wind. So we can see how the wind vector is affecting the airplane there. It's very important, like I said, to draw all the north, south, east, and west so that we can figure out what specific angles are and where they come from, okay, and how we get those values. Okay, so like the 59 degrees is important, right? Because north-south is 180 degrees. Well, 180 plus 59 is where the 239 comes from as well, right? That's the plane's bearing. So we're actually able to take 239, minus 180 to get the 59 degrees there. So that one's going to play an important role for us when we draw these out. Okay, and how everything is laid out, because we have two parallel lines cut by a transversal. That's what we're always looking for as well. So we know the both east-west lines are both parallel lines. They can be cut by our vector, okay? The vector B that's up here is just a vector that you draw, okay? It's a resultant vector from the effects of the wind and the airplane. Alright, so vector C represents the airspeed and bearing of the plane. Vector A represents the speed and direction of the wind when we draw those out. So essentially, we find SAB, alright? It's 239 minus 180. I went through all that with the 59. And then how we find EBF, it's 115 minus 90. So that's where the 25 comes in from. So I'll back up to there. See how there's the 115 minus 90? The north and the east make the 90. So 115 minus 90, that's where we get the 25 degrees from down there. Okay, so we can do these results. We can take 59 plus 65 and get 124. Use the law of cosines as you substitute in. Alright, we've walked through a lot of cosines multiple times. You should be able to get 446 as we go through there. Okay, so we're looking back. I'm going to skip back to the picture here for a second. Alright, so we can see where we just calculated A, B, C. Alright, so that's important because that's the resultant because of the wind and the plane. So that's the new bearing, alright, that the wind has to put an effect on the plane as it's flying. Alright, so now we need to find the resulting bearing B. We must find the measure of angle alpha, alright, in the figure, and then add it to 239. So using the law of sines, sine of alpha, alright, over 36 is equal to sine of 124 over 446. Alright, and when we substitute all that in, we get 4 degrees. Okay, so that's the resulting bearing of B is 4 degrees. Now we have to take that and add that to 239. So the total resulting bearing there is 243 degrees. Alright, because that's the new resultant because of wind. So hopefully we're able to see, I'm bumping back to kind of the diagram here. You can see that angle alpha is 4 degrees. Alright, so 239 plus 40. So that resultant vector A yields what we're doing with respect to the wind now. So the final answer is right, it's a magnitude of 446 at a bearing of 243 degrees. So that's how the wind can have an effect on an airplane as it's going through. Alright guys, well that's the end of this section. So as usual, email me if you have any questions or something's not working on your calculator or not. Those of you in class, let me know and we can go over some problems as well if you got questions. Else guys, have a great day. We'll talk to you soon.